Great, thank you. So we're going to move from Texas back to California, and I'm going to talk to you a little bit about some of our work, recent work in Los Angeles, looking at implementation and scenarios of best management practices to really look at meeting water quality compliance. But then we also look at kind of those ancillary benefits of putting those BMPs within the system. And so this project is funded by the Bureau of Sanitation in Los Angeles, and it's also supported by the National Science Foundation Engineering Research Center, which is actually talked about earlier in the session. Okay, so those of you that know Los Angeles understand that we get a lot of our water from basically upstream, right? Most of the water in Los Angeles, 80 to 90%, is imported, and that's highly variable depending on what year and the drought conditions within the system. But you can just see here kind of the network and how Los Angeles is really dependent on kind of these upstream sources, which, given the last drought over the last few years, have been very susceptible to change, which is a problem. So the graphic here shows basically that time series of total water used in Los Angeles over time in acre feet, and it basically shows the variability in that over time, and also then the sources of those various water supplies. So the LA Aqueduct is the Eastern Sierra Owens Valley, Metropolitan Water District is basically the Colorado River, and then this light yellow on the top here is kind of the local water supply, the local groundwater. And then you see kind of here towards the end, that's the recycled water or water that's being reused within the system, which has been very small up to now. You also notice that basically, given the last drought, we only got up to 2010 here with this data. You see that we're back down to levels that were kind of from the early 1990s when they implemented indoor water saving structures to really kind of bring down that total water use in the city. So given some of the conservation measures, and I talked about this yesterday in my talk, they've really been able to bring that water use, total water use back down. But there's still some issues. Because of the drought, the state, as many of you know, basically was under direction to really reduce their total water use by about 20% from the governor. And LA specifically put out a directorate about 2 months ago saying that they needed to reduce per capita potable water use by 20% within a few years, and then also a reduction in imported water by 50%, which is quite dramatic for the city that relies on so much water from the outside. So then everyone's working or struggling to basically come up with an integrated water strategy that really looks at basically all the risks in the system and then trying to improve the local supply within the system. So the question is, how do we get there? And this is from the Urban Water Management Plan for Los Angeles, and also just published produced in a publication that just came out in ASCE, which says LA is the blue-green city. So here's a pie chart of basically the current water supply within the system, the portfolio. And again, you see this, on average, the reliance on the LA Aqueduct, about 36%, Metropolitan Water District, about 50%, local groundwater, about 11%, and recycled water, pretty low. And this is what their portfolio, they want the portfolio to look like in about 20 years, in 2034. So again, you see this big reduction in the imported water from Metropolitan Water District, which is the Colorado River. You also see a slight reduction in the LA Aqueduct, but where you see over here, you see this big increase in local groundwater, recycled water, conservation efforts, another 9%. And then interestingly, they say stormwater capture should be 25,000 acre feet per year, and that's about 4% of this pie chart here. And then water transfers are, again, purchasing water from other sectors. But interestingly, if you do the math, 25,000 acre feet is about only 6% of the annual rainfall over the city of Los Angeles. To me, that seems pretty conservative. You know, if they would capture about 25% of the annual rainfall, you end up with about 100,000 acre feet of stormwater capture. So the question is, how hard or how easy is it to capture this rainfall in stormwater systems, and are we being too conservative, or what's the capacity? So a project that the city funded is called the LA Clean Water Sustainability Analysis, and it's really looking at LA's One Water vision. But our role in the project is really to look at kind of the TMDL compliance. That was the driver of much of this work, is how do we meet water quality, because Los Angeles is under orders to basically meet TMDLs. And then what are some of these ancillary benefits, which is we can decrease imported water by looking at more recharge, and can we still maintain flood protection or even improve flood protection if we put in some sort of stormwater capture system. And then other players on the project are basically looking at kind of the added value to health and safety, community parks, and open space. So we're doing the modeling part of this project, and this is our modeling roadmap. We're using SUSTAIN, which is the EPA's model that has basically SWIM and HSPF and some BMP implementation. We're looking at 3 watersheds within the LA Basin: Ballona Creek, Dominquez Channel, and the LA River. And again, the primary driver is the water quality compliance, looking at the different TMDLs in the different watershed systems, and then the ancillary benefits, as I talked about. And then overall in the project, they're looking at what are the economics of meeting these compliance, what are the benefits of that additional water, if there is any, and then how do we look at these 2 other streams of wastewater and other water in the system. So again, the modeling goals are really to look at BMPs that can help us meet TMDL compliance. And here's just a little bit of a statement about where the guidance they're under is basically saying that by 2016, 100% of the drainage areas within Ballona, the one I'm going to show you, has to meet dry weather waste loads, and 50% of the total drainage area has to meet wet weather. And we'll talk about what those are in a minute. And then in 2021, 100% of the drainage area has to meet both dry weather and wet weather waste load allocations. So that's a lot. I mean, in 7 years or so, they basically have to have 100% compliance. And then, so we want to, by putting those BMPs in to meet water quality, then we look at these other benefits, the costs associated with theirs, where these BMPs would be most effective, and looking at, which is not done all the time, at the watershed scale response of the BMPs, and then thinking about how will these perform under future conditions. Oops, I think I skipped a slide. Yep. So we're looking again at using the the SUSTAIN model, which is the SWIM model with the HSPF and Prince George BMPs, and then basically you have some optimizations within that model to look at where those BMPs should be distributed in the system and the cost associated with those BMPs. So there's 2 ways to run BMPs within SUSTAIN. You can do kind of discrete BMPs at the parcel level, or you can use this aggregate BMP framework, which basically takes runoff from different land cover areas and routes them to different types of BMPs. So for instance, if you look at high density residential, you can take certain areas of that and run it to a rain barrel, to a bioretention, to a dry infiltration basin, but then that dry infiltration basin may be getting runoff from other land cover types also. And so these are all aggregated, routed through the system, and then you look at the response at the outlet. There's several BMP options within the model. We're specifically looking at using infiltration trench and basin, dry pond, bioretention, vegetated swale, and porous pavement. We didn't look at some of these other ones. I know earlier in one of the talks, rain barrel was mentioned. But again, I really think some of these BMPs are climate area specific, and I'm not sure that rain barrel is the right thing for LA. As you know, most of the rain comes in the winter. You need the water in the summer, so the question becomes a maintenance and health hazard or health condition with rain barrels. So we did not optimize those. So our first initial work has been on Ballona watershed. It's about a 130 square mile watershed. We used 8 subbasins within the system to model it. It's been calibrated with USGS and LA County data right above the wetlands. We used event mean concentration data that was collected by the county and the city for water quality calibrations. And then the BMPs were calibrated using the Stormwater BMP database. Traditionally, this is what people do when they model. You can use the build-up wash-off or EMCs, and we use EMCs, and we got a better water quality calibration. So the TMDL scenarios that we ran, a little bit about those. Again, you can do a whole bunch of things in the model. One of the things that it's known for is running these optimizations of cost and BMP types and placement. So we ran that, and that's really optimizing the load reduction relative to cost. We also did some scenarios to look at kind of compliance, because one of the TMDL regulations says that if you capture the 3/4 inch storm, which is about the 85th percentile storm, you're in compliance. If you just capture that, no matter what happens, if you capture that 3/4 inch storm. So we wanted to see, do we meet compliance if we run that storm? So we looked at kind of regional infiltration BMPs, which are just capture all the water and infiltrate it, plus treat and release. We also looked at LID retrofit. So again, the ideal thing, if you know Elmer Street in Los Angeles, is to kind of retrofit the system, see if everyone has this nice kind of capture system within private property. So we looked at that scenario. And we also looked at public right-of-way runoff, and thinking if we just put BMPs along the public right-of-way, which is easy to do legally, how would that perform? So here's some results, and this is just kind of an overview of some of the scenarios. There's a poster this afternoon by Katie Radovich, a student that's primarily responsible for most of this work, and we can get more into the details there. But there's a lot of numbers on this graph, but here's those scenarios that we set up within the model. And here's the baseline run without any BMPs in the system, and there's very few in there now that actually are having any kind of impact. This is the percent of the area in the watershed that's routed to some sort of BMP. Then here's the BMP type that's in each scenario. So we've got here all kinds of BMPs, those 6 that I talked about are optimized within that, and we show the best Pareto solution of that. This one's just large infiltration trenches. The 3/4-inch storm was dry ponds for treat and release. And then in this one we have the vegetated swell, the bioretention, and porous pavement in these 2 that are down here. So when you look at the wet weather compliance and the dry weather compliance, again, wet weather is basically if there's a peak flow or a maximum flow of 64 cubic feet per second in that day, it's considered a wet day. If it's under that, it's 64 CFS, or under 64 CFS, it's considered a dry day. And they actually just changed these. They were at 40 CFS, but because there's so much dry weather flow in the system from irrigation, they upped these. And you can see the baseline exceedances currently, so you have about 28 days per year that exceed the current water quality standards, and during dry weather it's about 206 with the baseline runs. And that's out of about, I think, 500 wet weather days and 1,700 wet weather days. So still pretty significant, and theoretically they can get fined if there's sampling that occurs and they are over the TMDL compliance. So then you look at some of the optimization scenarios and you see basically a shift or a downward trend in the exceedances in the wet weather days. And mostly that's because now those days, because water is being captured, shift to dry weather days because you've got less water in the system. So you see a reduction in these, but you do see some significant, if you just do, for instance, the LID, you've only got a treatment volume of about 250 acre feet, and you see quite a few exceedances, almost the same as the baseline, and you actually see more dry weather days. And then what you see over here, again, is the copper load. We were doing TMDLs for metals, and you see the copper load reduction here. So again, this is the key thing here in meeting compliance, right, where that copper load falls and the concentration of the copper in the system. So the bottom line is basically it's really highly variable. We get some of the best results with these capturing the 3/4-inch storm, where we're capturing quite a bit, 80 to 90% of the watershed. Now the question becomes, of course, is that feasible? If you know Ballona watershed within the LA system, it's almost all urbanized, all developed. So if you really are going to try to capture, 3/4-inch storm, you'd basically have to put BMPs within, to capture 85% of the watershed. And is that feasible? Highly doubt it. Okay, ancillary benefits really quickly. We looked at potential for recharge. Again, the city says they need to capture 25,000 acre feet by 2034. Well, in these different scenarios, what is that potential recharge? And this is only water in our model that's coming right out of the top or the bottom of the model. So it's not that we're actually measuring recharge at the bottom. It doesn't have a groundwater modeling system in it. But this is the potential recharge coming out of the bottom of the model. And you see basically when you do the BMP optimization from 46,000, the lowest recharge is the treat and release is about 34,000 acre feet. And if you think about that, and this is just Ballona watershed, you have pretty significant potential recharge from putting in those BMPs. And so again, the question is we should be easily able to make this goal, if not more. Peak flow reduction. Again, this is a concern with putting in BMPs and trying to have more pervious land cover in the system is what are they really going to do for peak flow, peak flood reduction. And so what you see here is dividing up again by that 3/4-inch storm. The storms less than that, you see basically the range and reduction of the peak flood based on the type of BMP structure that's put in the model. And the larger storms, again, you see much more variable range, and you see the medium. So we still get some value in peak flow reduction, but again, if you have some of these larger ones, especially if you're doing treat and release, obviously you're not going to have as much peak flood reduction potential in the system. So I'll conclude on this slide and basically say that I think the goal of 25,000 acre feet stormwater use by 2030 is obviously doable. It's only 6% of the annual precipitation. So the question is that under-ambitious for the city's goals? Obviously, there's other factors to consider. Is what's the storage and how does that play into the regional groundwater plumes and things as far as contamination. But again, I think they've got some fairly realistic goals of stormwater capture. From our work with BMP implementation at the watershed scale, the treat and release have the best TMDL compliance, but really remove the smallest pollutant load per storm. The infiltration BMPs have a lot of capture, they provide better flood protection, but during smaller events, the pollutants are more concentrated and you have more exceedances. Recharge potential can be significant depending on design, but again, we've got a lot more to evaluate, which is design cost, which is quite significant. Space considerations, where do we put these things? We don't even think about land cost within LA, which is, of course, as you know, very expensive. And then you've got the operation and maintenance costs. So again, we're just looking at that just initial upfront physics of the system, but there's all these other things that we still have to consider. So with that, I'd be happy to take some questions.
Questions for Terry?